Got wood? We sure do. Buildings and structures are vital to our infrastructure and urban society. But in order for large structures, such as houses, to stand and remain sturdy, they need firm and stable internal frameworks. But what is the best material to make such frameworks out of in order for them to be the strongest, safest, and most cost-effective? Stability represents a fundamental problem in solid mechanics, which must be mastered to ensure the safety of structures against collapse. The importance of structure stability is evident from the history of structural collapses caused by neglect or misunderstanding of the stability aspects of design. Structure failures can result from too much stress from external forces, such as winds and earthquakes, or simply from the structure's own weight. In order for structures to be able to withstand stress forces, they must be both strong and elastic, able to remain sturdy and stationary, while also being able to return to equilibrium. When it comes to the internal structure of buildings, the materials most often used are steel and wood, often pine, both of which have their place and uses. However, in many cases, especially with small to medium-sized structures, wood has an advantage. Wood is one of the oldest materials humans have used for construction. Despite, and largely due to, its complex chemical nature, wood has excellent properties which lend themselves to construction. Wood is easily machinable, amenable to fabrication into an infinite variety of sizes and shapes using simple on-site building techniques, exceptionally strong relative to its weight, having a high tensile strength in comparison to its density, especially in comparison to steel, having a 120 to 170 tensile to density ratio versus steel's 30. It is also a good heat and electrical insulator, whereas steel is a conductor, which could result in greater loss of heat from a structure. And, of increasing importance, wood is a renewable and biodegradable resource. Woods have considerable elasticity and rather forgiving plastic deformation. Wood is viscoelastic, meaning it exhibits both viscous and elastic properties when under stress. Viscoelastic materials have a strain rate dependent on time. In other words, viscoelasticity means that it can bend quite far without having a deformity, as long as it is not bent for an extended period of time. The elasticity of wood and behavior of the plastic deformation are dependent upon various factors, such as the type, grade, moisture content, and temperature of the wood, with improving grades providing greater elasticity and overall strength.
The accepted safety factor for visually graded lumber is 1.3, and the safety factor for structural steel can be as much as 2. What allows wood to have this low safety factor is the fact that it is extremely flexible and can bend significantly before it deforms plastically. However, the end of the plastic region of the wood stress-strain graph is quite interesting. There is a harsh drop in the curve at the end of the region due to partial breaking of the wood. The wood splinters at this point, but still remains intact and bends after fracturing until the whole board separates. The data for this particular graph was taken when the wood was at 12% moisture content and 20 degrees Celsius. To arrive at the design values used in wood design, thousands of pieces of lumber of representative sizes, grades, and species have been tested. In a test of bending strength, for example, the values from a batch of lumber might range from 3,000 to 15,000 psi. By convention, the value of the 5th percentile is calculated. In other words, 95% of the pieces tested fall above this number, while 5% fall below. Choosing a value at the 5th percentile is a way of accounting for the wide variability in the strength of pieces of visually graded lumber.
The first part of the curve is a straight line, where the deflection is directly proportional to the load, and where once the load is removed, the beam will return to its original state. With increasing load, a limit point of proportionality is reached, after which the increase in amount of deflection is greater than the increase in load. But elasticity is still retained until an elastic limit is reached. If stress is further increased, the material loses elasticity and deforms plastically. At the point of maximum load, or ultimate strength, the material begins to yield and will fracture unless load is substantially reduced.
The strength of wood is almost entirely attributed to its microstructure. Wood includes chemicals such as lignin and hemicellulose. However, the main structural component of wood is cellulose. It is an organic molecule composed of carbon, hydrogen, and oxygen covalently bonded to one another. Because of its composition and structure, it forms chain polymers similar to plastics. This makes cellulose incredibly flexible and durable. Cellulose has a modulus between 134 and 136 gigapascals, giving it similar elasticity to some metals. The cellulose is formed into small box-like structures called cells. When alive, the cells are filled mainly with water, but are mostly dehydrated during processing. The majority of the wood's microstructure is made from long, longitudinal cells called tracheids. They conduct water vertically throughout the tree. Because of the growth process of the tree, 2 layers of tracheids of different densities are laid out every growing season. The softer, less dense layer is known as early wood or spring wood, while the harder and denser layer is called late wood or summer wood based on the time of year each grows. This is what causes the iconic tree rings. In addition to the tracheids and rings, radial structures known as rays strengthen the wood. These rays are much denser than the wood around them and stabilize the vertically oriented structure. Also, there are 2 main groups of wood, commonly known as softwoods and hardwoods. Hardwoods in general are more dense and have much larger variation in the size of the lumen, the region inside the tracheid. Wood structure gives it incredible strength with force applied longitudinally and flexibility under force applied radially. It is, however, relatively soft and can be cut easily. Because of its roughly cylindrical microstructure, it can withstand blunt impact longitudinally, but can easily be deformed by radial impact. Its main weakness, however, is it can be easily split down the middle from sharp force parallel to the grain. In this way, wood expresses anisotropy, similar to single crystals.
Cell structures are very strong. While they occur naturally in wood, because of their desirable properties, such substructures are fabricated from other materials to make stronger structures. An example of such use of natural structure is in cell structure reinforced walls constructed by Cellular Materials Incorporated, in which a honeycomb core is coated in face sheets, both made of aluminum, to create a very strong, lightweight, and stable surface.
The process of turning trees into lumber is fairly standard. The first part of the process is felling, where trees are inspected and marked to be cut down. The second part of the process is debarking and bucking, where the outer bark of the log is removed. The log is then cut to a template length using a bucking saw. Depending on the size of the log, it will be cut differently to optimize the number of resulting boards. Boards are later dried and planed. The next part of this process is trimming the lumber, where it will either be dried or seasoned to prevent decay. And the last part is grade stamping, where the lumber is visually and mechanically inspected and graded according to the amount of defects it contains. The 3 types of wood most commonly used are cedar, cypress, and pine. Cedar is used because it's light as commercial softwood and its low density enhances insulation value and makes it more easily to transport and handle. Cypress is used because it does not rot in extremely wet conditions, and pine is used because it's very common and found almost everywhere. One of the pros of building with wood is the cost. Wood framed steel buildings are less expensive up front, but pole buildings are cost effective if building dimensions fit within the wood frame of the building standards. Generally, pine wood is only 42 cents per square foot, and steel is between $16 and $20 per square foot. With cross-laminated timber, architects and engineers can design buildings 10 to 12 stories high made entirely out of wood. Earthquake testing in Japan showed that a 7-story CLT building survived high-magnitude earthquakes with very minimal damage. An example of modern ongoing construction that uses CLT is in the Limnologen project in Vaxo, Sweden. Recently, studies show that CLT structures are more energy efficient than carbon-intensive concrete. CLT has many benefits, the first of which is the design is flexible. Also, panels can be manufactured to precise tolerances. The third is there's an environmental advantage. The wood is manufactured using wood from sustainability managed forests, which means there's less waste. Also, fire protection. The thick cross-section gives valuable fire resistance because the panels char slowly.
It is important to remember that wood is not perfect. Wood is known to be hygroscopic, meaning that it will rot when it comes in contact with water. There are numerous cases where minor problems such as leakage can lead to major disasters. Ground contact can lead to decay as well as the introduction of wood deteriorating termites. Once a decay is discovered, immediate and major repair is required.